like Gauss's law. The trick of it is that what are we drawing as we go around? As I put a wire through there, you saw little magnets, all the compasses sitting around it. What am I drawing? Circle. I'm drawing circles. The magnetic field would be the same at equal distance out, correct? What am I containing? The wire. What's it? Is a wire without the wire by itself is going to create a magnetic field? Mr. Bernard, a wire just sitting by itself. What does a wire need to have? Doing what? Moving through it, because it always has electrons in a wire. Hopefully, something really odd is happening. Okay, so it says there's electrons traveling through it. We talk about that. We say that we call it current, right? So if there's current, then we have magnetic field. It's going to be the same for each circle going out from the center, right? Great. So if that's the case, then using that idea we just did with Gauss, we're going to say on the left-hand side, I'm going to have my current enclosed, right? And that's going to be equal to my closed integral, my magnetic field, dot dl. Now, I always use ds because that's what I grew up with. I will tell you what the next line looks like. Before I do that, though, I'm missing something. What am I missing? Somebody be intuitive. Give me what I'm missing. Cross is a good guess, but no, we're not missing that. Divided by mu naught. Turns out, because this was discovered not so long ago, we decided not to divide. We decided to multiply by mu naught. Make our lives better. Mu naught is on the formula sheet. Mu naught is, according to your formula sheet, it is 4 pi times 10 to the negative 7th. You might be thinking, Mr. Resney, why would they write it that way? Because you're going to divide by 4 pi an awful lot of the time. Certainly you're going to divide by 2 pi. And what are those units? Tesla meters divided by amps. Why would they do that? To cancel out the units, right? Cancel out the amperage and add myself to. So the Tesla meters, so if I flip this over, divide by this thing over here. Now, I will tell you this. You're always going to do the next line. In fact, oftentimes they don't even give you a point for doing this. Like in Gauss, they give you a point for doing this, for writing this down. The next line looks like this. It's going to be mu naught I enclosed equals B. What's the shape you're going to draw that is around a wire that would have an equal, it's always going to be a circle, right? Always going to be a circle. So life is good, because how do you find the magnetic field around a wire? The only thing we really care about? This is it. This is it. So far so good?
So it's like Gauss, except we don't have to find the shape every time.
Yeah, because there's only one shape, which is current flowing into a wire. Any other shape isn't going to work for us, symmetrically speaking. Which is okay, because frankly, wires are the only thing that does this. Now, there are going to be some times we're going to come up with a coil. Remember we talked about coils last time? Hopefully you did a couple problems on them. Coils do what? They create a magnetic field. We know this from the previous chapter. We also know, but why would a coil do that?
Because it's like a lot of wires.
It's a lot of wires. Basically, you're drawing the same loop over and over again. And if you take your finger, I use my left hand, that's bad. So let's say the current's going this way to the right, then it's going to curl. Each one curls the same way. It creates a very powerful magnetic field through the center going one way, and a very powerful magnetic field going the other way outside of the coil. Agreed? Make sense? And you can use your right hand to figure out which way it is. Because of that, all you have to do is do Biot-Savart for one of them. No, it's Savart. Ampere's law for one of them, and multiply that by the number of coils as long as they're closely packed. So the formula they came up with, which is a not perfect formula, doesn't work beautifully. But if you look at your formula here, you go, okay, so what would be the magnetic field? What you can do is, the formula is on there, it says BS, which is ironic because it's not biosmart. It's the magnetic field on a solenoid. Solenoid means coil. Is equal to mu naught I and then they use an N, and I'm always going to get this wrong because N drives me crazy. I learned this differently. So I'm trying my hardest to do it the way they do it. If you look on N, and I'm going to look at it right now, it's the number of loops per length. By length, they mean this direction, right? The more tightly packed the loops are, the more magnetic field you're going to get. The more loosely packed, the less magnetic field you're going to get. Does that make sense, Brandon? Okay. Now, what happened to my 4 pi, 2 pi? If we're talking about loops, we're talking about the length. We're talking about how long is a circle. Its circumference, right? 2 pi times the r, right? The r is what we're using here, the 2 pi r, so each one of the loops is canceled out each one. So each one would divide out one of these 2 pi r's, right? They'd cancel out, giving you just the number of loops, how many times you do it, divided by the length in this direction. Does that make sense? Sort of? All right. So you have problems to do. Go ahead and try number 12 first, and we'll see how we do, and then we'll work from there. We'll do 12, and we'll do 18 for certain. If you're done with 12, you think it was easy, go ahead and look at 18. IL cross B, right? So the I would be 15. The L is I don't know, but a bunch of those problems solve for force per unit length, so that's not really shocking that we don't know the L. We'll eventually move the L over. Cross B. I don't know the magnetic field. First of all, which way does the magnetic field operate? Because I got to worry about the cross product too. So you're going like this, but I'm going to use my right-hand rule and go like this, right? A second right-hand rule. And I'm going to put my thumb in the direction of the current. I'm going to notice that over here, it's going into the board. But as I turn my hand around, when I get to that wire, it's going out of the board. So at this point, it's coming right out of the board. Remember the decorations are a dot, like a dart coming at your forehead. The fins of the dart going away. Okay? So this is coming out. Is it exactly perpendicular? As long as these are parallel, it is exactly perpendicular, so the cross product is ignorable. Thank goodness. And I get 15. I'm going to move the L to the other side. My force of magnetism per unit length is going to be 15 times B. Agreed? Now, the reason this has a magnetic field at all is because of this wire here, right? So what magnetic field does this wire cause on this one over here? We're going to use Ampere's law, right? So I'm going to go mu naught I equals the integral of B dot dl, I think is what they use. dl, not ds. I should get rid of that dot. I don't even think there's a dot on their formula sheet, is there? Yeah, it is. Okay, never mind. Oh, wait, no? Yes, I use a dot. All right. Okay, and we know it's always going to do this. B times 2 pi r mu naught I. Agreed? So the magnetic field caused by that thing is going to be mu naught I over 2 pi r. So I'm going to fill out how much magnetic field this wire is causing on that one there. Just plug in everything, right? Mu naught, which is, we said from last time, it's 4 pi times 10 to the -7th. You're like, Again, why pi? Well, look what's on the bottom. What's going to be on the bottom every single stupid time? See that? Which is why they wrote it that way. The radius is 0.2, and the current from this wire is 10. Agreed? So then it's just a matter of canceling out my pi's. I've got a 4.1, so it becomes 0.1, 10, so just 1 times 10 to the negative 7th, which is weird because they made that work out really nicely, didn't they? So my force of magnetism times length, this gets to be 1 times 10 to the negative, nope, I'm lying. It'd be 1 times 10 to the negative 5th, isn't it? And so this becomes 15 times 1 times 10 to the negative 5th, because that's the magnetic field. So I get 1.5 times 10 to the negative 4th newtons per meter. Now notice something. Yep.
Weren't you doing the left wire?
I was doing what the left wire does magnetism-wise on the right wire. Okay? So the B is being created on this wire here, right? We're talking about what's the force of this wire here? Force of this would be IL times the magnetic field it is feeling. Why does it have a magnetic field on it? Because this other wire exists and is doing stuff to it. Without this, there's no magnetic field at all. Right? So it's just this one doing to this one. So we find the magnetic field by using the second wire and how it affects the first wire. Does that make sense? And then we just IL cross B, that one. Okay, mid-sentence, I lost my train of thought. Notice something interesting. The magnetic field caused by a 10 amp wire, is 10 amp produce a lot of current? It's enough to kill you. It's a sufficient amount. 15, a little bit more. They're 0.2 meters apart, they're this far apart, right? And the force is what? Magnetic fields forces are very small. I had a wall about half the length of this covered with electronics to make a single magnetic pulse, and it was hardly enough to suck the watch off my arm. I mean, at UCI, we were going to let. We could turn this thing on, messed up our Apple IIe, but other than that, it wasn't strong at all. And yet we were pumping water through that thing because we were running averages of 700 amps, 800 amps to get the thing to go, right? And just to make a small little, almost microscopic sample shake inside the machine. So magnetic forces are very, very small compared to the other ones we're running into. Okay, so the same land as gravity. Good? All right, try 13 then. 13 has a different question, but much the same sort of tools.